So today I want to largely talk about two things, and these are an example of where conformal field theories arise in condensed matter physics, and then another example in where they arise in just quantum mechanics. So we'll be talking about the idea of classical and quantum phase transitions in condensed matter and statistical physics, if you want, and particularly simple but still non-trivial example of a conformal field theory in zero spatial dimension in one time dimension. So this is a quantum mechanics problem, and this is the idea of conformal quantum mechanics. And it's a simple enough problem that it's exactly solvable. So we can solve the system both classically and quantum mechanically. I refer you to my statement about what it means to solve a quantum mechanics problem in terms of computing correlation functions. And today I'll just outline some of the symmetries of this system. So we're not going to be actually solving the problem, but what we are going to be doing is setting the stage for we're going to be setting the stage for this quantum mechanics problem that I'm going to come back to again and again, because it is such a simple problem that we can illustrate a lot of. We want to learn about conformal field theory by studying. So when I introduce the idea of conformal blocks, for example, and conformal block expansion, I'll be talking about it in the context of conformal quantum mechanics, and because we'll be able to do all the calculations explicitly, and I'll leave the more general setting as an exercise. All right. And speaking about the symmetry of the problem, I'll introduce a conformal symmetry in this quantum mechanics problem, and it will basically just be the conformal group S2R. So it's the set of 2 by 2 matrices with unit determinant real entries, and I'll show you how the generators of the conformal symmetry for this quantum mechanics problem are the same as a set of 2 by 2 or 3 by 3 orthogonal matrices with unit determinants. All right, so that's the game plan for today. So let me start off by this specific about which was, as you remember, price cookers, because they have particularly interesting physics applications, and there were two particularly interesting points that we noted. Was that a rice cooker made use of two things. One was the liquid gas transition in water, and the other one was the ferromagnet paramagnet transition in magnets. When you combine those two things together, you get this little gizmo that doesn't burn your rice. Okay, so there are certainly practical applications to conformal field theory. So the liquid gas transition in water is an example of a classical phase transition, as is the Curie point in magnets, the transition where a magnet becomes demagnetized at some temperature. And the fact that there is a non-zero temperature is really key to this story. Okay? These are examples of classical phase transitions. They're not the only type of phase transition. There's also quantum phase transition. And we will come back to quantum phase transition a little later when we study the Ising model. And in particular, I'm interested in the description where the phase transition takes place. That's what we call a critical point, and there are classical critical points and quantum critical points. Okay. Let me be a little more precise about what I mean by a phase transition. So mathematically, a phase transition is a point in the parameter space of the theory at which free energy becomes a non-analytic function of one or more of its parameters. So phase transition is a point in phase space at which the free energy of the system free energy F minus 1 over beta times the logarithm of the completion function becomes a non-analytic function of one or more of its parameters. Beta here is the temperature. And Z the partition function. Any statistical or thermodynamics, then you know that this thing here is the central object that we want to calculate in statistical mechanics, partition function. Once you know what the partition function is, all of the thermodynamic variables in your system can be computed from the partition function. In previous years, this course was really focused on computing Z, because when we calculate Z, it's by calculating the path integral. And so we did a lot of work on computing path integrals, various theories, and then analytics continuing the path integral, you get a partition function for a Euclidean theory. The Euclidean theory is the same as finite temperature theory, blah, blah, blah. I'm not really that interested in partition function or this. Just trying to motivate why formal field theories are important in this setting. We will come back to calculating the path integral much later in the theory, but we can do a lot more before that. Phase transitions in such systems are classified by their order. The order counts the order of the derivative of the free energy that is discontinuous. So, for example, if the first derivative of the free energy is discontinuous, then you call this the first order phase transition. If the first derivative is continuous, but the second derivative is not discontinuous, then you call it the second order phase transition. And this is in the what's called the Landau paradigm for phase transition. So phase transitions classified by the order. This is the same as the order of the derivative that is continuous. So again, a point in the phase space at which such a transition takes place is what's called a critical point. And part of this game is working out how close to a critical point we are in the phase space. Okay. And we can decide our proximity to the critical point by measuring something called correlation length. Correlation length is the length at which the degrees of freedom in a system are correlated with each other. In other words, interact with each other in a particular way. And of course, these are all nice words, but if I'm talking about correlation length or whatever, I need to calculate, I need to give you something to calculate. The thing that you calculate to determine the correlation length is the 2-point correlation function of some set of degrees of freedom. So let's take a step back. I'll give you a theory. There are some dynamical variables in the theory. It's a quantum theory, and as such, the objects that you can calculate, the observables that you can calculate, are correlating functions, what we'll call correlators of the theory. There are various ways of calculating these correlation functions. They're the same type of correlation functions that statisticians calculate when they study various things. They want to know how elements of the theory are correlated with each other. They want to know how these elements of the theory talk to each other. So in a quantum theory, whether it's quantum mechanics, whether it's quantum field theory, whether it's string theory, the objects that you can calculate are precisely these correlation functions. Okay. The thing is that in a conformal field theory, these correlation functions take a very specific form that's dictated by the symmetry theory. Right? But I don't know anything else. I don't even have to go calculate these things. If I have a conformal field theory in my hand, I can tell you what the functional dependence of the correlation functions are, just because it's a conformal field theory and there's this large class of symmetries that are highly tightly constrained here. Okay. So to compute the correlation length theory or inner theories. Okay, 2-point function. So, for example, suppose I give you some statistical mechanical system with some set of degrees, let's call it sigma. I don't really care whether it's bosonic or Gaussian or whatever. I have some set of degrees of freedom, I'm going to call them sigma. So, for example, the function of sigma at some point x space. Again, this x could refer to spatial variables, refer to space-time variables. I don't really care, but I'm interested in the functional form. So this 2-point function will have 2 arguments, sigma at different points, typically x and y. Might as well select y to be the origin. Again, it doesn't really matter. And this is what's called the 2-point function. If I have one variable, like this, and I calculate the expectation value of that variable, then that's called a 1-point function. And since I've got 2 of these guys, I can calculate 2 1-point functions like this. So 2 expectation values, 2 quantum average of one. The expectation value is a quantum average. I can calculate it in many different ways. One way to calculate it is through this particle that I talked about. And if I subtract off these like this gives me what's called the connected 2-point function. In a sense, the connected 2-point function is like calculating the variance. Okay, it's what's called the variance or connected point function. Okay. And for those of you that are doing the quantum field theory or the quantum mechanics, we've done about Feynman diagrams. This particular object corresponds to a particular set of Feynman diagrams for the theory. It's what's called connected Feynman diagrams, a set of Feynman diagrams that are essentially mnemonics for calculating these quantities and the variance next to 2.5 selects the set of, if you want, physical diagrams from the set of all diagrams. Okay. The thing that I want to talk about is that this guy here has a very particular form for a field. Looks like this. It goes like the distance that exits from the origin, so 1x is some constant power times e to the minus 1x over some number psi. Right? So this is in a CFT. And this guy here, this psi, is called the correlation length. And it measures how the various degrees of freedom in the theory talk to each other, over what length scale do they talk to each other. Sorry. Let's go. The statement here is not that in a CFT. It's I'll tell you what happens in a CFT. So in a quantum field theory, this connected two-point object has a particular form. And then to determine how far we are from this critical point, what we do is we vary parameters of the theory, for example, the pressure or temperature, or in the case of a magnet, the external magnetic field. And then I measure how the degrees of freedom in the theory are correlated with each other by calculating this object. Okay. At a critical point, this psi, the correlation length, goes to infinity. So 1 over psi goes to 0. And if you calculate in natural units, you'll see that 1 over psi has the units of a mass. So it's a scale in the problem. Right? So when psi goes to infinity, when these degrees of freedom talk to each other over an infinite range in this system, right? 1 over psi, the mass scale in the problem, the natural scale in this problem goes to 0. So there is no scale in the problem. If there's no scale in the problem, then the system is scale invariant. If the system is scale invariant, and you zoom in and out, and no scale makes any difference, then we're talking about conformal field theory. This is why conformal field theories emerge at critical points. So let me do one concrete example to illustrate what it is I'm saying. So, as an example, right here, you consider a ferromagnet in an external magnetic field. So what are the microscopics of this system? Essentially, I've got a bunch of electrons in a metallic material, magnetic material, and these electrons have some magnetic moment. That magnetic moment you can think of as a spin. The spin is in any direction on the sphere. Right? So take any direction on the sphere. When the material is magnetic, a whole bunch of these spins all align and point in a particular direction. When they point in that particular direction, that's when I have a magnetic material. Right? for a demagnetized material or paramagnetic material or material that has no magnetism at all, there's no alignment on average of the spin. So the average over the entire material spin is zero. Okay? When the spin is not zero, the average spin is not zero, then I have a magnetic material. So I have a bunch of these spins, right? This. And if they're aligned, then I have a magnetic material. If on average they're not aligned, then I don't have a magnetic material. Right? And the point with the ferromagnet to paramagnet transition is that if I turn up the temperature of the system, then the electrons that contribute to this these magnetic moments to the spins start to fluctuate, right? And they fluctuate more and more and more the higher I crank up the temperature until I get past a certain point where the fluctuations are basically over the entire material. And if I average over the entire material, then the net fluctuation is zero. Okay, at that point, that temperature is the Curie temperature beyond which material is not magnetic anymore. Right? So that's the microscopics of what happens with this magnet. So what we want to do is consider some material, ferromagnetic material, in an external magnetic field. So consider a ferromagnet in an external magnetic field. And the point here is, if I have an external magnetic field, then the spins are influenced by that magnetic field, and they tend to align or anti-align depending on the material that I'm talking about with that external magnetic field. So typically when people talk about these kinds of materials, what they do is they write down some Hamiltonian, and in that Hamiltonian will have some terms that correspond to the blue arrows and some terms that correspond to the interaction between the external magnetic field and the blue arrows. Okay. So one example of this kind of material is something called the Heisenberg XXX spin chain. It's a chain of spins that models a magnet. The Heisenberg model in certain circumstances also model similar kind of things. The dialable parameter in our system is going to be the temperature of the system. So what we're going to do is think of the temperature as a dial that we tune in a continuous way, and we watch what the system does as we crank up or down the temperature of the system. Okay. And the point here is that as the temperature approaches this critical temperature, the Curie temperature, the thermal fluctuations in spin degrees of freedom become larger and larger. The average magnetization goes to zero. When that happens, there's a transition of the subject from a ferromagnet, so where it's magnetic, to a paramagnet where it's no longer magnetic. And you can test this with an actual bond magnet. Take it, you heat it up, and find that past a certain temperature, it stops becoming magnetic. Well, this is what happens when it stops becoming magnetic. So essentially, what happens here is that the correlation length, the sky side, goes to infinity. Okay, all the spins correlate with all the spins of the entire material. So let me try and make some of these note that more complicated. Okay, So the basic degrees of freedom are the individual spins of the magnetic moments. Okay. So this would be some variable which I'll call F, function of where the magnetic material is on. Okay, it's what we call an order parameter. So, as the temperature approaches the critical temperature, Curie temperature, this would be Curie temperature of the magnet. The spins correlate over the entire material. And the correlation length psi becomes infinite, which means that 1 over psi goes to 0. And the theory of the order parameter, these S's, becomes massless and scale invariant. And the massless scale invariant theory is a conformal field theory. So in the thermodynamic limits, this chain of spins becomes a field theory. And in the limit where 1 over psi goes to 0, that field theory becomes a conformal field theory. So again, I'm just using words. Right? I haven't told you how to calculate anything at this point. Right? I haven't even told you anything about the relationship of these things. Okay. And my goal here in this example is not to do that. To need a lot of machinery before we can get to that point. It's just to show you kind of what behavior to expect of systems like this. And then we're going to go all the way to that, and we're going to study symmetries. We're going to study what I mean by symmetries, what I mean by conformal symmetry, how we perform symmetry by interpreting in the quantum mechanics theory, what the difference between classical symmetry and quantum symmetry is. So don't freak out that these words are unfamiliar. We're going to build up the dictionary as we're going to go along. But I want you to keep in mind what's going on here, and then as we slowly develop this machinery for dealing with it, I want you to refer back to these examples, and hopefully they start to become clearer and clearer as we go along. Okay, so what are the thermodynamic properties spoken? The thermodynamic properties of interest in this system are a couple. One is the correlation length. The other one is the free energy. Yes, we wrote down above. Then there are quantities that are derived from the free energy, like the magnetization. Material. And the magnetization of the material is just the derivative, it's the rate of change of free energy with respect to the external magnetic field. On the one side. Then there's a quantity called the magnetic susceptibility. Which is traditionally called chi. And chi is the second derivative, so that's dm by dx. And for example, the heat capacity of the material, which is C, and C is minus T times second derivative of the energy with respect to the temperature. Okay, this is created in terms of detail and the plus temperature, but this is what it is. Okay. And typically in the thermodynamic limit of this spin chain, the order parameter that we work with is the magnetization. This guy M. So M is a function of X, and we keep track of what's going on with this variable M. It's not a fundamental variable. If you want fundamental variables in this problem are these spins. It's an effective variable that describes the physics of the system. Right? The magnetization, the order parameter in the problem. And we can parameterize our proximity, how close we are to the critical point, by some dimensionless quantity that we construct out of the temperature. So we're going to parameterize proximity to criticality by the variable tau. Tau is defined as T minus critical over T. Okay. Sorry, over TC. Okay. So, in terms of tau, these thermodynamic quantities behave in a particular way. In terms of tau, the correlation length goes like tau to the minus mu, some variable mu. The heat capacity goes like tau to the minus alpha. The susceptibility goes like tau to the minus gamma, and the magnetization goes like minus tau to the minus beta, and three-point function M X and 0, remember M is our order parameter, goes like X to the 2 minus the dimension plus minus some eta. Alpha, beta, gamma is actually a delta as well. Also goes like H to the another delta. All these big letters are what we call critical exponents. And these are the quantities that statistical mechanics care about. And the key thing is that you can compute the critical exponents directly from the scaling dimension of the operators of the conformal field theory. Okay, so these are all what are called critical exponents. they dictate the behavior of the thermodynamic variables of the system at criticality. These are the variables, this is the behavior that you care about. But what conformal field theory does, it gives you a way to calculate these critical exponents directly from the scaling dimensions of the various operators in the field. Okay, so those are a lot of words, but the key thing out of this is that the description of the system at the critical point is a conformal field theory. So a lot of the developments of conformal field theory back in the 1970s, 80s, 90s came from people doing statistical mechanics. Okay, and there was this big interplay between people doing statistical mechanics and high energy theorists who picked up that a lot of these things are applicable to things like string theory. And right now, there's an enormous amount of interplay between two fields. And this is pretty much it. This is really why it's the case. Now, one thing I would like you to keep in mind is that the thing that we're tuning in this system, the dial in our system, is the temperature. Right? And whatever we're talking about is taking place in non-zero temperatures. This is an example of what's called a classical phase transition. And a classical critical point. There are also different types of critical points where the fluctuations involved are not thermal fluctuations of the degrees of freedom. Right? These fluctuations, the specific degrees of freedom, come because of cranking up the temperature. Right? And they're thermal fluctuations. They're fluctuations that are determined by the non-zero temperatures. There are another type of problems in which the type of fluctuations that we're talking about are fundamentally quantum fluctuations. These critical points take place at zero temperature. They are the cutting edge of condensed matter physics, statistical mechanics. It's trying to understand the properties of matter at zero temperature critical points, where quantum phase transitions take place around quantum critical points. Right? There is a beautiful set of lectures that's available online by Sylvia Sachdev, who is really one of the key players in these ideas. And they are working through a book that I think has just come out. Yeah, I think it's come out. So there are in fact two books by Sachdev. One is called Quantum Critical Points, the other one is called Quantum Phase Transitions. And they capture a lot of this material. So if you want a relatively advanced treatment of the subject, then Sachdev's books on quantum critical points and quantum phase transitions will take a look. But there's also a one semester course that he gave at the Institute of Study last semester, and that details this, if you would like to take a look. Yeah.
Since correlation will be higher in the line, does not mean you will perfect line.
No, that's sorry. That's probably not the best way to the point is that it's not that these are talking to each other over
What is the correlation? I guess I'm asking.
well, what it means is that this 2-point function only scales like this. There's no exponential drop off. Okay. All right. So our goal in the next couple of lectures is going to be to understand the formal transformations of the formal symmetry in any number of dimensions. But before we do that, I want to say two things. One is that amongst all the number of dimensions that are possible for formal symmetries, 2 spatial dimensions is spectral. And 2 spatial dimensions is spectral for a reason that will become apparent as we go along. But it also allows us to phrase everything in terms of complexity. So in fact, for those of you who've done a course in complex analysis, the word conformal would have appeared in that context, where you would have seen that there are these things called special conformal transformations that are a combination of translations and inversions, and these special conformal transformations are exactly one of the generators of the conformal. Yeah. So in 2 dimensions, things become particularly simple because I can phrase everything in terms of complex variable theory. And one particular notion that appears again and again and again is the idea of an analytic function or a holomorphic function. Turns out that conformal fields are just holomorphic functions for the complex plane. Okay. So we'll spend a lot of time talking about 2-dimensional theories for 2 reasons. One is that reason that we write everything in terms of complex analysis. So all the tools that we've learned in complex analysis, some of you last semester, will come into play. Right? So you've already got the mathematical toolkit to work with. The second reason is because especially in this course, which is a complex and string theory course, string theory is just one of these 2-dimensional conformal fields, right? That might not gel with some of the words that we've heard about string theory and 10 dimensions and stuff. But the thing that I'm talking about here is the world sheet of the string. So if you take a 1-dimensional object, trace it out in space-time, it leaves behind a 2-dimensional sheet. That 2-dimensional sheet in this context is called world sheet, and it turns out that string theory is nothing but a 2-dimensional conformal field. So a lot of what we're going to say, even though it's applicable to higher dimensions, we're going to focus on the 2-dimensional case for those 2 reasons. But before we do that, even I want to focus on 1 dimension. So 1 space-time dimension. So 0 space, 1 time. So the conformal quantum mechanics is a formal in 0 plus 1 dimension. And you might think, yeah, 0 plus 1 dimension, what is there to really talk about? That's possibly an oversimplified system. In fact, it turns out that even though it is a very simplified system, it is very much polynomial. It's a particularly useful polynomial because it's a solvable system. We can solve it exactly, quantum mechanically as well as technically. But a lot of what we learn in the 0 plus 1 dimensional quantum mechanics problem is portable to higher dimensions. Not everything, because it is oversimplified, but a lot of it carries through. So the basic variable in this problem is, I'm going to call Q, and Q is going to be a function of T. There's only 1 dimension, 1 independent dimension in the problem, and that's time. There's no spatial dependence at all. Right? All the physics in this problem is taking place at 1 point in space. And in this theory, Poincare symmetry is exactly the same thing as time translated symmetry. So to look for a Lagrangian that is Poincare symmetric means looking for a Lagrangian that is time translation invariant as well as scale invariant. And scale invariance in this system is what's going to be performance of the first. Okay, so Poincare invariance, Poincare symmetry. Same as time translation symmetry. And Lagrangian theory is going to look like this. The kinetic term is going to be half Q by dt squared, Q dot squared, and the potential is just minus d over 2 Q squared. So it has a Q little minus 2 dependence on it. That's a bit unusual from what you might have seen in the first course in quantum mechanics. At this point, there's no restriction on the sign of the constant, but when G is positive, everything goes to nicely. When G is negative, all hell breaks loose. Think a little bit more carefully about what happens. But at this point, there's no restriction on phi. As an exercise for you, I'd like you to work out how does it run? Give you the critical model. Pretty straightforward exercise. Point here is that we've constructed, by construction, this theory is time translation and scale invariance. But it turns out that it's actually invariant under a bigger set of symmetries. And this is conformal transformation. And conformal transformation of the time coordinate. So, by way of comment, there is a variant of the conformal transformations. We include the scale invariance as well as the time translation invariance of operator invariance, and under which time coordinate T goes to let's say T prime. Prime is A T plus B over C T plus D. Again, think back to what you learned in complex variables theory. This is not clear. Simultaneously, we have to change Q. Prime is Q over C plus D. And the restriction that we have is that AD minus BC. Well, what this means is that we can represent dangerous. Take form A, B, C, D with the determinant of A is A minus BC 1. In other words, the set of 2 by 2 matrices, real entries and unit determinant, which is what we call special linear group. Go on. Okay, so I've done abstract algebra. This is called the special linear group of 2 by 2 matrices. With real entries. Special again, on the fact that the determinant is 1, and the R to the real entry, 2 to working matrices. And any conformal transformation in one dimension, one space by dimension, is of the same is of this form, which means that we can identify the conformal group in D equals 1 with SL2R. Okay. Formal group in D with 1. So we label this guy with formal quantum mechanics. Thanks, guys. So that the action associated with this, so S is the integral of the time of L conformal quantum mechanics is invariant under SL2R transformations. Possibly up to some total derivative terms. Okay. So this means I would like you to take SL2R transformation, which I transformation with this form, apply it to that Lagrangian, show that at worst that Lagrangian will change by some term that looks like d by dt or something, right? So total derivative. The action is invariant under SL2R transformation formula. What do these conformal transformations of this form actually do? To understand what they do, is actually homomorphic from 1. So if you come 1 instead of 3 plus 1 is 3 by 3 matrices that are all orthogonal, that's the O, and the S special means that they also have unit determinant. Okay. The reason why I want to make this identification because SO2,1 is the set of Poincare transformations. Then I can go to the generators of the Poincare group, and this is something familiar, and so I can identify what the physics of it. The only question is whether I have enough time. I think the answer is no. So let me stop here today. And on Wednesday, we will make the identification. On Wednesday, we'll make the identification. and finish out the section. And then we'll start the next section on more general mathematics.